Hi everyone, and now we'll be talking about random variables. A random variable is a concept in statistics and probability that assigns numerical values to the outcomes of a random process. Random variables can be classified into two types: discrete random variables and continuous random variables. A discrete random variable takes on distinct countable values. Examples include the number of heads in a series of coin flips, the result of rolling a die, or the number of students passing an exam. On the other hand, a continuous random variable can take on any value within a range, making it uncountable. Examples include the temperature in a city on a given day, the weight of a newborn baby, or the time taken to run a marathon. Understanding the distinction between discrete and continuous random variables is essential for analyzing data and calculating probabilities in different contexts. And now let's dive deeper into different types of random variables. A discrete random variable is a type of variable that takes on a finite or a countably infinite number of distinct values. These values are separate and distinct, often representing specific outcomes of an event or counts of occurrences. Each possible value is associated with a probability, forming a clear and enumerated probability distribution. For example, let the random variable x represent the number of students who pass an exam. The possible values of x might range from p of x equals 0, the probability is that no students pass, to p of x equals 1, the probability is that exactly one student passes. P of x equals 2 will represent the probability that 2 students pass, and so on, up to p of x equals 20, representing the probability that all 20 students pass the exam. This enumeration allows us to map the likelihood of each outcome clearly and systematically, showcasing the fundamental property of discrete random variables: their ability to describe countable, distinct outcomes in a mathematically structured way. This chart represents a binomial distribution for the number of students passing an exam, where the probability of success p is equal to 0.6. The binomial distribution models the probability of obtaining a fixed number of success, k, in a series of n independent trials, each with the same probability of success. The probability mass function is denoted on the slide, where a kind of nk tuple in the beginning represents the number of ways to select k success from n trials. In this case, this distribution reflects the likelihood of different outcomes, such as the probability that exactly 10, 12, or 14 students pass the exam. The chart picks around the most probable number of success, illustrating the central tendency of the distribution. This visual helps us to understand how outcomes are distributed when p equals 0.6 and the number of trials n is fixed. A continuous random variable is a variable that can take any value within a defined range, with probability is described by a smooth probability density function, or PDF. Unlike discrete random variables where probabilities are assigned to individual values, the PDF represents the density of values at any given point, showing where outcomes are more or less likely. Probabilities for continuous random variables are determined as the area under the curve over a specific range, not at exact points. Consider an example. Let the random variable x represent the time in hours a runner takes to complete a marathon. The probability distribution might look like this, where p of x being within range 3.5 to 4 represents the likelihood the runner finishes between 3.5 and 4 hours, while probability that x being in the range 4 and 4.5 captures the probability of finishing between 4 and 4.5 hours. Since the distribution is continuous, the probability of finished at an exact time such as p of x equals 4 is 0 because individual points have no area. This highlights the unique property of continuous distributions. Probabilities exist only over intervals, as the total area under the PDF curve sums up to 1. The chart illustrates the Gaussian distribution applied to a continuous random variable, specifically the time in hours the runner takes to finish a marathon. The formula of Gaussian distribution is depicted below. This example effectively demonstrates how the normal distribution models continuous random variables, with an example grounded in a real-world context. Thank you for watching, guys. If you enjoyed this video, hit the subscribe button for more awesome videos. See you in the next one.